So, up to this point, we've looked at the kinematics in one dimension, whether that one dimension was the horizontal, the vertical, or even up or down some slope. As long as the motion was along a straight line, regardless of which direction that straight line was, 1D kinematics was sufficient for us to describe what was happening after some initial conditions. We've also looked at vectors and how to deal with two-dimensional quantities and how to do math with those vectors compared to vectors that go in different directions. And so now we can combine both of those concepts together to look at our first type of two-dimensional kinematic motion. And I say our first type because there are two types of two-dimensional kinematics. The first one is the one you probably most often think about, and that is projectile motion. Incidentally, the second one is rotational motion, but that's for another video. And so projectile motion. How are we going to define projectile motion? Well, we are familiar with throwing something straight up. This was the concept of free fall. If we throw something straight up, comes straight down. We throw something downwards, or we throw something, or just drop something. In each of those cases, we're talking about free fall, up and down. Things get more complicated when we're not just going up and down. When suddenly we have some amount of velocity that's going in the horizontal at the same time as having some vertical motion. And so this time we're not along the ground, we're not going straight up and down. We're going to see what happens if we have some motion in the air that has a horizontal component to it. And so we can do a quick example of that. So again, if I have this hockey puck right here, and I give it a velocity straight in this direction, let's see what happens to its subsequent motion. And so what we saw was a motion that went like this. And that is a different shape than the type of motion we've experienced up until this time. That is part of projectile motion. Now, usually when we think about projectile motion, we often think of something being thrown and caught at the same height. So for example, if I throw this in this direction and I catch it at the same height, you see that motion of a projectile going like this. And so what does it take to create projectile motion? Can I throw something this way and it's projectile motion? Yes. Can I throw something upwards in this sort of diagonal direction? Is that projectile motion? Yes. And one more. Actually, you can throw something downwards, and that's projectile motion too. Not straight downwards. There always has to be a horizontal velocity component. So as long as there's some speed in this direction, your vertical speed doesn't matter. Could be up, could be down, could be straight sideways. So here I go, a little bit higher. And so this time I threw the object with an initial velocity downwards, but gravity still played a role in dragging it down even further. And so the motion wasn't a diagonal line. No. It was, again, that projectile. And so all of these types of motion are considered projectile motion, and we will figure out how to handle these types of problems in this video. So let's define projectile motion with words to begin with. Let's define projectile motion as the motion of an object that has some initial velocity of which at least some must be in the horizontal direction. oops, the horizontal direction. And so what we mean by that is when we have our object and it has a velocity, some of that velocity has to be at least this way. The reason is because if there is no horizontal velocity, then you just have free fall. Then everything is happening up and down. You have to have some initial condition such the velocity is this way. And then there's more. The addition to that is once you have that initial velocity, the subsequent motion of our object must follow a path dictated by gravity alone. Okay, so there we go. So again, what that means for us is the projectile is governed by gravity. Gravity is what's accelerating our projectile, nothing else. This isn't the motion of an airplane. This isn't the motion of a drone. This is the motion of an object that is freely moving through the lower part of Earth's gravitational field here on the surface of the Earth, and it can't be going straight up and down. This straight up and down is free fall. Any kind of motion that way is projectile motion. And so whether, again, I throw something downwards like that, as long as it's got some horizontal velocity component, or the more traditional projectile motion like that. These are all examples of projectile motion. It's kind of fun. Anyway, and so we ask ourselves, well, what equations are going to be needed for us to solve equations that have projectile motion in them? Well, our kinematic equations that we derived, we originally derived them in the x direction, but we quickly realized that they were applying to all directions, and overall they do work in 2 dimensions. These are our 2-dimensional equations. Let me give it a nice title here. So let's rewrite those 1D equations in 2 dimensions. And so that means we have VF equals V initial plus AT, not in the X, not in the Y, but in general. And so that's why we're using our vector notation there, representing 2-dimensional vectors. And we can rewrite our equation number 2. This time we're not doing it in terms of X, we'll do it in terms of S, a general direction. All right, and finally, our third equation, Vf squared is equal to V initial squared plus 2 times acceleration subtracted by our displacement, which is our SF minus SI vectors. All right, so that's great looking at those equations. You're like, hey, I know how to use those. This should be easy, but there's a little bit of a problem. You can't actually use those equations in this form. You can't use these equations if our vectors are going in different directions. So for example, if our SF vector and our SI vector are going in different directions, you can add them with each other. Same thing with velocity and acceleration. Basically, what I'm trying to say is these equations are only used in individual dimensions. And so if you have an object that's moving through 2-dimensional space, both with an X and a Y component, you actually have to use these equations in their original 1-dimensional form, in the X direction and the Y direction. You can't use these equations to solve two-dimensional quantities. You have to break them down into components and then use our one-dimensional equations to solve your unknowns. And sometimes you have to put things back together or recompose them. And so that's what we learned in our vector lesson. So we know that we cannot use these equations for vectors that go in different directions. Can't just use VF squared equals V initial squared is equal to or plus 2A SF minus S initial if all those vectors are going in various directions. These equations only work if everything is going in the same direction. And so what we do is we decompose. So we will decompose all of our vectors in projectile motion. We'll decompose all of our vectors into their x and y components. And I'm labeling those axes x and y. You could label them whatever you want, but traditionally we use the horizontal as always for x and y the vertical. And then we apply our equations. Now, I could just give you these original equations and you can write your x and y equations from them, but why don't we do that? Why don't we actually write it ourselves so that you see what it is? But you don't necessarily need to rely on what we're about to write down. You can yourself go back to the original kinematic equations and write them from the S direction as you need them. But just so we do it once here, you know how to do it. So kinematics in 2 dimensions in the x and y direction. Now you might be saying, well, that was weird. We had the equations in 1 dimension in the x and the y, then you put them into 2 dimensions into the vectors, and now you're putting them back into the x and the y. Well, essentially, yes, but these equations are simultaneous equations. What I'm about to write down is happening at the same time, as I will demonstrate soon enough. And so the first thing that we want to understand is what the acceleration is in the x and the y direction. And so think about it for a second. What is ax in projectile motion? What is ay in projectile motion? Well, let's think about it. If I throw this object like so, and you see its motion, was it accelerating in the x direction? Did it get faster in the x direction after it left my hand? No, absolutely not. And if you neglect air resistance, it didn't get slower either. It actually has a constant speed in the x. There's no acceleration in this direction when it's traveling through the air. And so it'll actually maintain its speed in the x direction. So ax is equal to 0. That's nice. I like when the acceleration is equal to 0, constant speed, super easy to understand. And then what about ay? What was the acceleration in the y direction? Yeah, absolutely, right? Gravity. Gravity is the acceleration. And so it's equal to g, whether it's positive or negative, depends on how you set up your problem. And so let's just say that we'll just throw on some absolute value signs there, just so we have, just so it allows us to do plus or minus. I guess another way we could write it, maybe it's better, is this could be plus or minus, depending on which way you have set as your positive direction. All right, let's write these equations down. The x one is the easier one. I'll start there. Okay, so I'm writing the x direction equations where the acceleration is equal to 0. So I go here, and my first equation, well, if a is equal to 0, it just says that vf is equal to v initial. All that's saying is that velocity is constant in the x direction. Okay, that's fine. That can be our first equation. V final x is equal to v initial x, where the acceleration is equal to a. All right, so that's velocity. Let's go to our second equation. Hopefully that'll be at least a little bit more useful. And it is. The second equation with the acceleration equal to 0 still gives us something fairly interesting. And so once again, we take that second equation and write it as x final equals x initial plus v initial x times time. And that's it, because the third equation isn't going to give us anything different. If we set a equal to 0 here, clearly you still just get vf equals v initial. So we'll leave that one out. Okay, that's it for the x direction. Y direction is going to be much more similar to a regular one-dimensional kinematic stuff that we've talked about in the past. And so we'll just write this as equation 1, equation 2, equation 1 for this one is going to look like this. Vfy equals v initial y plus, and I'm just going to keep it as ay, simply because the g again could be positive or negative. I don't want to write plus or minus into the equation. I'm just going to keep this as ayt. But you know that its magnitude is certainly the same as the magnitude of the acceleration due to gravity. Our second equation becomes y final equals y initial plus v initial yt, so far the same, but let's not forget our last term, 1/2 at squared, because this time again we do have an acceleration, just putting it up there. All right, so our third equation this time is valid and useful, so let's write that down as vfy squared equals v initial y squared plus 2 times the acceleration in the y direction, y final minus y initial. And that's it. That's it. That gives us our kinematic equations for projectile motion. And we've used all these equations before. And so you think to yourself, well, this should be easy. It should be easy. And an important part of it staying easy is going to be you bookkeeping that you have what you have. You know what you have and you're able to use it. What do I mean by that? Basically, notice all the sublabels, the fy's, the initial y's, the fx's, and the initial x's. This is where it becomes very, very important that you keep track of what direction your quantities are governing. So for example, if I have a v initial velocity and I give it to you and I give an angle and you break that down into its x and its y components, we have to keep track of those. You have to keep track of those, and that's why it is so important for us to do proper labeling when we're doing projectile motion. We may have been in one-dimensional kinematics not caring so much about labeling things sub x and sub y because there was only one dimension. We should have actually got the habit at that point, because now it's super important for us to be able to tell things apart. The other hard part about these projectile motion problems is going to be the step 1 and the last step. And the first step is going to be to decompose our vectors. The in-between stuff will be the same as it's always been. It's just applying these kinematic equations in the x and the y direction, which we've done before. And then finally, the last step is going to be to recompose our answers, as we'll see soon enough. All right, so here is a picture of the motion of a parabolic object, so something undergoing projectile motion. A lot of people are familiar with this diagram, especially if they've taken any high school physics. And so we'll go over what some of the terms are, but this diagram is not going to end up being that useful for us, because What this is showing is projectile motion that takes off and stops at the same height. That's a very, very specific type of projectile motion, and it doesn't allow us to universally talk about all types of projectile motion, which is what I want us to be able to do. But so we'll start with this and then we'll get more general. And so in this projectile, again, what's happening is our projectile is starting over here at the 0 position. It is launched with a velocity. That velocity has a magnitude, but it also has a direction. The direction, as always, is measured from the positive x direction in the counterclockwise direction, and that gives us our initial velocity. Now, that initial velocity has some horizontal component to it. That means there is an x component to that initial velocity, absolutely. And so we have projectile motion. And so everything that happens after that launch, everything that we see with this motion after that is due simply to gravity. Gravity is what determines the subsequent motion after we give it its initial conditions. What are its initial conditions? Well, just its position and its velocity. And we're going to set its initial position to 0 like we're used to doing. X initial equals 0, Y initial equals 0. Give it an initial velocity and then see what happens. Now, where we stop this problem is also at the same height. And so over here, you can see that we end up at the same Y position that we started from, basically the ground. And at the ground, we have some final velocity. Now, what is that final velocity? If you were to say, throw a football and it goes through a projectile motion and your friend catches it at the exact same height, what is the final velocity of the football? Some of you thinking it's 0. It's not 0. Once again, we're not talking about what happens after it's caught. We're not talking about before it's thrown. We only care about the instant after it's thrown and the instant before it's caught. And so our final velocity is not 0. It is, in fact, magnitude-wise, we'll find out, is exactly the same as the initial velocity. They will have the same velocities since we're at the same height. The x component doesn't change. The y component changes significantly. It goes up and it comes back down again. And we're used to projectiles that go up and down. If I throw something straight up in the air at 1 meter per second and I catch it at the same height, well, gravity has slowed it down to 0 and then it sped it back up to 1. It sped it back up to the same velocity at the same height. If it would continue to fall, it would get faster and faster. But at that height, it has the same speed. And velocity, same speed, not velocity, because the initial velocity was up, the final velocity is down. Same thing happens here. The magnitude of that velocity is going to be the same as our initial. But we'll see that as we go. But this location here, or I guess at the start here, we can call this x final, y final. In case that's confusing, let me move it all the way to the end. So we'll have our y final position right there, and there's our arrow. There we go. Okay, and so a couple other important parts of this parabola. One is the maximum height. The maximum height in this case does occur halfway between the two, but that's only because it lands at the same height that it's launched at. If this was a more complicated problem where our final position was a little bit higher, a lot lower, anything like that, y max could occur at different places. Similarly, the range. A range is a famous value that again gives us how far our projectile motion went. But again, range is a term that's only used when you are launching and landing at the same height. And so it doesn't actually have much use for us at all because we want to learn very general values. And so we don't care about range. What we care about is y final. In this case, y final is equal to range, but in many other more complicated problems, it will not be. But now what I've started to see, what's made this picture very useful for me, is that I'm starting to see how the x and the y component are related to each other. It's the x and the y component that go together simultaneously for us to actually see the projectile motion, to see the parabola. That's the shape of this motion. And so what we are starting to realize is that two-dimensional projectile motion is actually just a combination of two one-dimensional motions that are happening at the same time. And those two one-dimensional motions are, of course, free fall, up and down, and a constant horizontal velocity. Let's put those two things together. I'll do another page here. We'll say that 2D projectile motion is just a combination of two one-dimensional motions. And those two one-dimensional motions are happening at the same time. They share time. And we can see that in our list of equations. The only thing that the x and the y direction share with one another, the only term on either of those two sides that is the same is time. Time, t. That's the same t on the x and the y. It's happening simultaneously. It's going to be the key to solving so many of the projectile motion problems that we encounter. And so what does it take? What two 1D motions am I talking about? Talking about free fall, going up and coming back down. Normal free fall motion, if I was to throw something up in the air and catch it at the same height. So let's write that, free fall. And I'm going to add that free fall at the same time. I'm going to have constant horizontal motion, no acceleration. Just motion in the horizontal happening at the same time. And when I put those two together, what do I get? A perfect parabola. Pretty good parabola. And that is projectile motion. All right, so we see it up there now. And what we ask ourselves is, can we reproduce that sort of motion? Can we do a little demonstration that shows us how free fall is combined with constant horizontal motion? Let's take a look.
So in this recording, we have Rupinder throwing a ball straight up in the air, demonstrating free fall. Now he's not moving, and what we're going to see now in slow motion is that he begins to run, and he's going to quickly reach a constant velocity. He'll have a constant speed, and he's going to throw that ball straight up into the air again trying to do free fall. But now he has a horizontal velocity component to his run. So the ball goes straight up, but it doesn't just go straight up and straight down. Because it was already moving to the left on your screen, it ends up undergoing projectile motion, showing that projectile motion is just a combination of free fall and a horizontal constant velocity.
Now let's go ahead and do our very first example of a projectile motion problem. And let's do one where we start and land at the same height, just to get us started in this area. And we're going to do a problem with a long jumper. in the Olympics. And so let's say in the 2016 Olympics, Summer Olympics. All right. And so the long jump is an event where somebody's running really, really quickly. They get to a mark, they jump off, and they see how far they can go. And they're a projectile the entire time. From the instant they leave the start line, basically from when they take their jump off the board, they have an initial velocity with a direction and a magnitude. Gravity then dictates what they do after that, and eventually they land. And when they hit the ground, that is the location of their final X position, and that distance is what's going to be marked as their length of their jump. So a long jumper in the 2016 Summer Olympics leaves the ground at, let's say, 8.50 meters per second at an angle of 38 degrees above the horizontal. That's the common way to describe that angle in just regular words. We have a horizontal in the positive X direction. It doesn't really matter which way, but it's the horizontal, and it's 38 degrees above that. And so your question is, how far did she jump? And just for fun, what place did she come in? Compare this result to the real scores of the 2016 women's long jump, and let's take a look at how our fiction athlete does. Okay, and so let's draw a picture. And this is the first time that we're drawing our projectile motion picture. The projectile motion picture is in some ways very similar to that of our one-dimensional problem, where we want to show our initial position, we want to show our final position, we want to show our positive X and Y directions, etc. I'm going to start by drawing my axes and in defining which way I choose positive to be. I'm going to say plus Y is up and plus X is in the direction. You can choose whatever you like, but I think that's a very logical assumption. And I'm going to give an initial velocity like that. That initial velocity we call VI. And there's going to be an angle theta above the horizontal that it launches at. And then you don't have to draw this in-between part, but basically what happens is a projectile. And eventually our object, in this case jumper, ends up here. And so now let's write down what we actually know about what's happening from this problem. The obvious one that's given is the initial velocity. So let's start there. The initial velocity is 8.50 meters per second, 38 degrees above the horizontal in the direction that we care about, the counterclockwise. That's good. What else do we know? Well, let's look at acceleration. The acceleration for projectile motions is always the same. AX equals 0, AY, in this case, because we said plus Y was up, is negative, let me give that negative another try, negative 9.80 meters per second squared, because the acceleration is in the downwards direction. Now let's start writing our positions right onto our graph. And I'm going to start my problem, as I always do, at 0. I'm going to say the X initial is equal to 0, and so is the Y initial equal to 0. That's where I'm starting this problem. And then obviously both the X and the Y increase. Eventually the Y goes to its peak over here, and comes back down and ends at the same height that we started from. So we actually know y final as well. This is great. Y final equals 0. In case you're not sure, you can extend this line as well. Maybe a little too far. And see that it does hit the ground. The x final, on the other hand, that's unknown. That's what we're actually looking for here. We want to see how far away she jumped. And do I know anything else? I think that's it. I don't have any time information. I don't have any final velocity information at this time. And so let's start this sort of problem by decomposing all the vectors we need to. Now notice the acceleration is already decomposed into its x and its y values, so that's great. It's this v initial we have to decompose right away. So let's decompose v initial. I can't do any mathematics on the v initial until it's in its x and its y components. As we all know and learned from trig, our x component, well, that would be this one right here. So I can decompose it into its x and its y. I'm going to erase that in a second. So this is v initial x. This is v initial y. We can get v initial x because it's the value that is adjacent to the angle. And so adjacent, if you remember your trig, is cosine. And so that's v initial cosine of theta. While v initial y is going to be equal to v initial sine theta. Now at this time, you could calculate your values for v initial x and v initial y as numbers, and then just keep v initial x and v initial y in your equation, keep it for your algebra, and eventually at the end, substitute your final number in. That's totally fine. I think just for fun, I'm going to keep my v initial x and my v initial y as v initial cos theta and v initial sine theta. I'm not going to put any numbers in now. I'll put in the numbers at the last step. And so I'll keep it cosine theta and sine theta. All right. So let's jump into this problem. What are we going to do to find out the unknown? We are looking for x final. Can we find x final by doing kinematics only in the x direction right now? No. I don't have enough information in the x direction. Let's see what I know in the x direction. I don't know t. I don't know x final. And so, unfortunately, if I look at my x equations, that's not going to be good enough. There's not that many x equations, if you recall. If you look at my x equations over there, it says x final equals x initial v initial x times t. I don't know t, and I don't know x final. I got two unknowns in that problem. And what that means is that even though I realize that this x value is what I'm looking for in this problem, I can't find it because I don't have enough information. But we're lucky because one of the things that we don't know about is t, the time. Remember that time is shared by both the x direction and the y direction. And so what that means is or I could ask myself, could I find time in the y direction and then use it in equation 2 in the x direction to get my x final? And the answer is yes. And the answer is always yes. What we find in these projectile motion equations is very, very often it's time that we have to find first. And we have to find it in the direction where we know more stuff. And that's usually the direction, almost always the direction, where we're not looking for an unknown value. Notice that I have y final. I don't have x final, but I have y final. Y final is 0. And so what that means is I know more stuff in the y direction than I do in the x direction. So I'm going to use the y direction to find the one unknown that I can use in the x direction, and that's time. So that's my strategy here. Let's use the y direction to calculate t. Once I have t, then I'll put it into equation 2. So out of the y direction equations now, which one can I use given what I've been given? Given what I've been given. Yes, I don't have v fy in this problem. I have everything else, and so equation 2 is going to be the equation that I use. Since we don't have v final, we're not asked to find v final, let's see if equation 2 is going to help us. So our motivation, we're going the y direction, and we're trying to find out time, because we know that's going to help us get to our final answer. So the equation that we choose is 2, where we say y final equals y initial plus v initial yt plus 1/2 ay t squared. And so now all we have to do is do a little bit of algebra. Let's zero the terms that we know are 0. We've got some nice bookkeeping here. Y initial equals 0, y final equals 0. That's it. And we're concentrating on getting time. So we have that 0 equals v initial y divided times t plus 1/2 a t squared. Now make sure you're not dropping your sub y's here and here. It's going to be very important to keep everything together. I'll move my v initial y to the other side. And that's just equal to 1/2 ay t squared. I can divide both sides by t. So dividing that by t gets rid of that one and that one there. And finally, I am solving for t, and so I have this 1/2 ay, which I will divide through by that term, leaving me with negative. In fact, why don't we just leave it like that? So we have negative 2 v initial y, all divided by ay. And this is equal to t, the time. And so let's finish this problem off by putting in our equation for time. Remember that v initial y we've already determined was vi sine theta. So this becomes minus 2 vi sine of theta, all divided by the acceleration in the y. Throw the numbers in and let's see what we get for the time. It's going to be necessary for our next one. Some people might think, well, should I just take this into my next equation? It's going to start to get really messy. So let's find a number here. That's 2 times, what do we say, 8.50 times the sine of 38 degrees, all divided by minus 9.80. And there was a negative out here as well. So we've got 2 negatives that are going to cancel each other out. And we get our calculator going here and see what we get. Make sure you're doing this as well. And I get a time close to 1 second, but I'm going to keep a lot of digits here. I do 3 sig figs, so at least keep 4 digits around. So 1.06. Eight. That should be good enough. 1.068. Yes, very nice. And that's in seconds. All right. So now that we have the time it takes to basically make the jump in the y direction, we know that's the exact same time it takes in the x direction to go from x initial to x final. And so let's find out what that value is very, very simply. And we will again use equation 2. But this time in the x direction. So the x direction, we're looking for x final. And our second equation, this time written in its x form, is that x final equals x initial plus v initial x times t. Now you know that's the case. That's all you have. But it's very, I think, logical to write it fully out to show where that came from. So I always like to write out the full equation, knowing, of course, that ax is equal to 0. There's no acceleration in the x direction. Also, we set our initial position equal to 0, leaving us a super easy equation of xf equals v initial xt. And we've already figured out that v initial x was vi cos of theta, I guess again still multiplied by t, giving us our final value of x, final jump position. Let's take 8.50 cosine of 38 times our time. What was that? 1.068. Giving us our final x position. Let's see what we get. Okay, very impressive. 7.15 meters. Amazing. And actually very, very realistic. Remember, the question asked you not just to find this value, but also to tell me what medal she obtained in the Olympics. I'll look it up here on this. It's not really any calculator. And the answer is, if you want to look it up yourself, please pause the video. That is the silver medal. And so she's tied with the person who won the silver medal, or maybe she is that person. And there we go, 7.15 meters.